So today's speaker is Kevin Trenberth, and most of you, Kevin doesn't need much of an introduction, but if I was to give him his full introduction, it would be like all 5 of these pages. So I won't do that. I'll do the edited highlights instead. So Kevin is from New Zealand originally, and he graduated from Massachusetts with his PhD in 1972. He's been a lead author on at least three IPCC reports, and therefore has obviously been a winner of the Nobel Peace Prize. He's a chair of GWEX. He's on the scientific steering committee for CLIVAR and the World Climate Research Programme. He's a distinguished senior scientist at NCAR. He's a fellow of the American Meteorological Society, the American Association for the Advancement of Science, the AGU, and he's an honorary fellow of the Royal Society of New Zealand, who have higher standards than everybody else. And he won the Jewel G. Charney Award from the AMS and the NCAR Distinguished Achievement Award in 2003. And his most recent award, which is presumably the one he's been waiting for most, was the Prince Sultan bin Abdulaziz International Prize for Water. So, anyway, the floor is all yours, Kevin.
Thank you. Thank you, Rosie. All right. This talk is very much about climate change and global warming. And it really relates to what global warming is. And I will suggest to you one way of thinking about it is through the Earth's energy imbalance. This figure down here indicates the schematic flow of energy through the climate system coming in from the sun, the outgoing long-wave radiation to space, the distribution with latitude, and the consequences in terms of jet streams and weather systems. A lot implied in that figure that transport heat polewards. This is an overall flow of energy through the climate system. On the left-hand side of the figure is the absorbed solar radiation, the difference between the incoming and the reflected. And on the right-hand side is the outgoing long-wave radiation. And in an unchanging climate, overall, the absorbed solar radiation and the outgoing long-wave radiation are in balance. However, with climate change, with global warming in particular, we introduce the increases in greenhouse gases, heat-trapping gases on the right-hand side here, which cuts down on the outgoing long-wave radiation. And so there's an imbalance which gives you a net global heating. And so that is one way of thinking about global warming, is that the warming really means heating, and then that heat has to go somewhere. How do we measure this energy imbalance? Firstly, there are direct measurements from space. These are from now the Ceres instrument and previously from the Earth Radiation Budget experiment of the absorbed solar radiation, the outgoing long-wave radiation, and the net. You can also take an inventory of where all of the energy has gone, and we can also use climate models with specified forcings, and we can also maybe use atmospheric reanalyses. So a brief commentary on these methods is that the first one is not accurate enough in terms of absolute values, but it may be very good for the relative changes over time. The second method of taking the inventory I've labeled as being best overall, because it's the only way we can really get the absolute values. But is there some energy missing? Have we got a full inventory of everything that's going on? And there are issues with the changes over time because of the changing observing system. The third one depends on how good the model is and how good the forcings are, the specified forcings. And atmospheric reanalyses for this purpose are useless because they have inadequate forcings. There's no treatment of aerosols in atmospheric reanalyses. There's no representation of things like Mount Pinatubo eruptions. And they also don't conserve energy. And so I'm not going to talk any more about that, although we have figures related to that. So where does the heat go if we're taking an inventory? Firstly, it warms the land and the atmosphere. Secondly, it goes into the ocean. There's heat storage within the ocean, which contributes to sea level rise. It also melts land ice, glaciers, and the ice sheets, Greenland, and raises sea level. It can also melt sea ice and warms the melted water. I've distinguished that from the land ice melting because this does not contribute to sea level rise. And also, it contributes to the hydrological cycle. It evaporates moisture. There's more rainstorms and cloud, which therefore can change the albedo and therefore alter the radiative imbalance at the top of the atmosphere. And so this is also an important consideration. Over 90% of the energy, though, goes into the ocean. And so the ocean heat content turns out to be a very important factor here. I'm first going to look, though, at CCSM4. And here we have specified forcings from increased greenhouse gases, changes in the sun, volcanoes, and aerosols. And you can actually get a pretty good idea as to the forcings that have gone into the CCSM5, the CMIP5 runs, in this case from CCSM4. If you just look at the clear sky shortwave radiation at the top of the atmosphere in the tropics, and you can see over time the big volcanic events in the past and then in more recent times, and also the gradual increase in aerosols in the troposphere that are playing a role in the overall forcings. However, you'll notice there are not any small volcanoes, for instance, in recent times. So when we look at the CCSM4, this is an 8-member ensemble result from 1850 on, and the last section here, which I've sort of done in orange, is blown up down the bottom. So this is just a replication of this last piece blown up, and I've identified the main volcanic eruptions on here, Agung, El Chichón, and Pinatubo. And what I've shown here is the overall net energy imbalance at the top of the atmosphere as the ensemble mean, which we can track over time, plus and minus one standard deviation. The one standard deviation varies over time among these 8 values. And the standard deviation is 0.62 watts per square meter. This is quite a large value when you think about it, you know. So the radiation, the energy imbalance at the top of the atmosphere, even in an unchanging climate, say back in here, is still fluctuating from day to day. Within a month, with a value with monthly values of 0.62 watts per square meter. That's quite large. Now we can also take 12-month running means, which is what I've done here, and I'm showing you all of these ensemble members here. You can see them much better down the bottom here, and here you'll see that they all fit within this, pretty well all fit within this 1-month standard deviation. And if you take the standard deviation of the 12-month running mean about the ensemble mean, the standard deviation is 0.25 watts per square meter. And so we've beaten down the 0.62 for an individual month to 0.25 for a 12-month running mean. So it's not quite a square root of 12, which you might expect if the fluctuations were completely random. And in fact, you can see here that there's interannual variability that's occurring. And of course, we expect that from things like El Nino events and decadal variability, all of the other things that are going on in the climate system. And so, but nonetheless, there is a lot of high frequency stuff that's going on related to the weather, related to changes in cloudiness that affect the top of the atmosphere energy imbalance and therefore global warming. Notice also the values that we get out of CCSM4 in recent times, in the 2000s, are averaging somewhere around 0.9 watts per square meter. Now, if we look at Mauna Loa, in particular at the El Chichón eruption, we can see that, in fact, there's several eruptions given here. They're at different latitudes, and this one was at a latitude much closer to Hawaii than the others. But there was a very sharp response. And the general estimation of when this volcano went off is that the dispersion of the aerosol was really quite rapid. In the model, however, it's nowhere near as rapid, and it's idealized. And so the eruption went off here, and then this is actually courtesy of Andrew, and we can see that the peak in the optical depth, the mass mixing ratio, actually occurs about some 6 months after the volcanic eruption. And this seems to be especially a problem with the El Chichón eruption, as I'll show you later on. And you can also see that the whole profile here is fairly idealized. In addition, one of the things that's missing in the CCSM4 runs are all of these volcanoes that have occurred in the 2000 era. So later on, I'm going to show you the series results, and so this is relevant to that. This is the optical depth here, and the biggest one was a volcano here somewhere around late 2006. You might remember this time frame from when I show you the series results later on, 2007. This is the biggest one here, and none of these are included. None of these aerosol effects are included in the CCSM4 runs. There's also changes in the sun going on, and during the 2000s, we went from an active sun to a very quiet period, especially from about 2003 on to 2009, and then we've gone into a more active phase in recent times. And this is all expressed in terms of the radiative forcing, not the total solar irradiance. So there's the albedo effect and the geometry is taken into account. And so the amplitude here in terms of radiative forcing or the fluctuations are within about 0.15 watts per square meter. So these also play a role, and I'm assuming, I haven't checked, I'm assuming these are included in the CCSM4 at least to some degree. I don't know how idealized they are. So looking now at ocean heat content, and in particular some work that we have done which is already published and which made it onto the cover of GRL. This cover picture actually shows an Argo float here and a ship that deployed the Argo float along with some time series of the ocean heat content on here and also all over the cover. And so this work has been published, but I'll show you a little bit of that. Now, when we're dealing with ocean heat content, one of the problems is the changing ocean observing system. And this is a summary of that overall, down to 400 meters, how many observations there are, down to 700 meters, and down to 1,700 meters. And there was a big increase after about 2004 when the Argo ray was established. And you can see this in the northern hemisphere and the southern hemisphere. Southern hemisphere in particular, rather devoid of observations before then. And here you can see, there's some observations back in here at greater depths. And since the changes are relatively slow, then even having a few observations helps to pin down what was going on, at least in the northern hemisphere, back in these earlier times. And otherwise, the observations are going down to about 500 meters, which is when you've got the expendable bathythermographs. And then prior to about 1970, things really fall off. And so the confidence in any analysis prior to 1970, I think, is very low. Another factor is that one penchant of some of the oceanographers is not to use models. And so they've just analyzed Argo data. There's at least two prominent sets of analyses, or three, that have just used Argo data. But Argo data is far from complete. There are no observations in the Indonesian region at all. Coastal regions are missing. The Gulf of Mexico and the Caribbean are not well observed by Argo, and there are some other spots, odd spots, where these floats haven't gone. In this region, the ocean is relatively shallow, but still it plays an important role in El Nino. And by leaving this region out, the variations are in error by order 0.1 watts per square meter on an interannual basis. So, and so just using Argo data is actually not the way to go. Whoops, I did it again. Go away. So we're going to use ocean reanalyses, and this is the ocean reanalysis from ECMWF, ORAS4. There's a complete documentation of this in the Quarterly Journal in 2013. And there are perturbed initial states and perturbed forcings that go into the reanalysis so that 5-member ensemble values are generated. So instead of a single result, there are actually 5 results that come out of this. It starts in 1958. It uses this model here with a little bit on the resolution here. It's bias corrected using the most recent data period, and it uses surface fluxes from the ECMWF reanalyses, and it also assimilates sea surface temperatures. It includes altimetry from 1992 on, and is much more comprehensive than any analysis based on Argo data alone. So here's the results of this, looking down to 300 meters. This is what it looks like, and there are 5 curves on here. This is going down to 700 meters, the time series. There's a base period back in here, which is why they all agree in this fairly early period here. And then this is going down to the bottom of the ocean. And so there's a number of fascinating features in this record of the ocean heat content. Firstly, you can certainly see that there's an overall increase after about 1970. So this is global warming, one manifestation of global warming, but there's also some quite strong fluctuations in here that we need to pay some attention to. Mount Agung went off in 1963, and I've marked El Chichón and Pinatubo here, and it turns out these really sharp dips in the ocean heat content are associated with these 3 volcanic events. And they stand out really well, as I will show you subsequently, in this particular record, unlike in any other ocean heat content record that exists. In addition, I've highlighted on here the 1997-98 El Nino event as being one where something strange is going on, and there is a dip in the ocean heat content at a number of different levels here. And then we can also see that there's some really sharp increases in recent times in the 2000s in the ocean heat content. Well, this is the overall slope here gives you the rate of increase in watts per square meter on a global basis. And so if we also add here this 1 watt per square meter in the recent times, you can see that in the early 2000s, the rate was actually exceeding 1 watt per square meter for a number of years, and then it's fallen off a bit in more recent times in the total depth analysis. But we can also see that there's this so-called hiatus, a pause in the warming that's especially manifested in the top 300 meters of the ocean. And so I want to explore that and the differences that are going on here in some depth as we move forward here. Firstly, if we break down the global mean into the extratropics as the solid curves, and then the tropics into the tropical Atlantic, Pacific, and Indian Ocean, and look especially at this time of the 97-98 El Nino, we can see that the green curve shows a large, very sharp drop. And so there was a huge amount of heat lost in the ocean throughout this 1997-98 event. And of course, this is why 1998 was such a warm year. All of the heat was coming out of the ocean, making this an exceptionally warm year, the warmest year in the 20th century. And we can also see on the dotted blue curve that this was mainly in the tropical Pacific Ocean. So this was indeed associated with the El Nino event. Now, if we take the annual means of the ocean heat content down to 700 meters, this is what it looks like in comparison with ORAS4 and a bunch of others. And you can see that there's an overall warming that they all agreed to after about 1970, but my goodness, they're all over the place. Now here we've actually lined them up in the Argo era, so that by definition they're sort of lined up here to some extent, and you can see this flattening out that's this hiatus in warming that's occurred. But boy, there's a lot of discrepancies in this. And the thing we're interested in is the rates of change of this, so we want to differentiate this, and this turns out to be problematic. And and we only have, for the most part, annual values available. The Dominguez one is a 3-year running mean, so it's a bit smoother than the others. That's an overall slope of 0.5 watts per square meter. So if we simply take a one-sided difference to get the rates of change, this is what it looks like. It's a god-awful mess. And this is going down to 700 meters. If you take differences, it's automatically a high-pass filter, and it puts an artificial spectral peak at 2 delta, in other words, 2-year time period. And so you see this sawtooth character up and down, which is characteristic of taking simple differences to get the rates of change. So this is not the way to do things. Instead, what we've done here is to smooth it with a 1-2-1 smoother, and now the values are settling down somewhat, but still we don't think this is the best product you can get out of these things. And so if we take the ORAS4 data, where we've got higher resolution, and we look at the annual mean values as the cross points, and then we've got a 12-month running mean on here as well, and then we take differences and do a 1-2-1 smoothing, and what we've done, decided to do ultimately, is to do centered differences rather than one-sided differences, and then you can see the result. We've lost quite a lot, especially at times when there's really sharp peaks, like in here with El Chichón. But actually, I'm surprised at how well this method actually works. But this is about what you can expect to get out of these other ocean analyses, since we only have annual data to work with. So here's what we think is our best estimate of the rates of change from all of these different products, and the ORAS4 is in here. So these are the annual values of the rates of change. And so here the scale is, plus or minus 1 watt per square meter, which is, at least in the ballpark of what we might expect, whereas, the original scale was plus or minus, 3 or 4 watts per square meter, totally unrealistic physically. Now, I've also marked the volcanoes on here, and you can see, amazingly, back here in the 1960s, there's a dip in quite a number of these ocean analyses or reanalyses, which is really quite remarkable in many ways, given how poor the observing network was at that time. There's a lot of scatter at the time of El Chichón, and I think there's some good reasons for some of that, but I'll come back to that in a little bit more. It's partly related to the sharpness of the drop, but when that occurs is all over the place in these different analyses. And then if we look at Pinatubo, again, there's 3 or 4 analyses which sort of have a dip in about the right place, but there are some, like the Hadley Center model, that's the Palmer one, which is at the wrong time. This is the World Ocean Atlas result going down to the full column compared with the ORAS4. You can see the overall warming is about the same. But the features, all of these features that we expect to see associated with the volcanic events, and in association with El Nino events for that matter, are completely missing in the World Ocean Atlas data, and it relates to their rather shoddy treatment of the data, I would say. So, looking now at the ORAS4, this is looking at the top 700 meters. This is the time series of the ocean heat content. And down the bottom, I've got the rates of change of this as 12-month running means, but now we can do this continuously over time. And you can see now the 5-member ensembles are showing up much more than they show up here in the ocean heat content itself. And so the perturbations and the forcings are revealing themselves a bit more in these rates of change. Now, when we go down to the full depth, I put these in behind the blue curves, and you can see that they line up pretty well here through to about 1998. And after 1998, you can see the full depth ocean rates of change emerging, and so there's a significant difference in the heating occurring after about the 1998 El Nino, as it turns out. Now, this is the times of the 2 volcanic eruptions. here's Pinatubo, and here's El Chichón. Now, this is 12-month running means, as I've said, and so the volcano went off in March of 1982, and so because we've got a 12-month running mean, it starts to see that 5 months ahead of time. So this is occurring a little bit early, but in the raw data, which is somewhat noisy, then indeed the drop occurs almost instantaneously in March and April of 1982. The difference between these after 1998 and in the 2000s is 0.21 watts per square meter, going into the deeper part of the ocean here. Now, this is one of the key slides that I want to show you. What I'm showing you now is the expectations that we got from CCSM4 in terms of the overall radiative forcing and the response of the model, which is the solid curve, the ensemble mean, plus or minus 1 standard deviation of the monthly means, along with the 5 curves from ORAS4 here. Firstly, let's look at the volcanic eruptions. Here's Agung. Pretty amazing agreement, really. And Pinatubo, actually, I think this is excellent agreement as well. This is the only ocean heat content data set which has this kind of agreement with what you might have expected from the radiative forcing with what actually happened. But when we look at El Chichón, we can see, look at this offset here. It's rather interesting. Now, certainly, what happened in ORAS4 occurs very, very quickly. But as I showed you earlier on, the response function, the way in which it was put into CCSM4, has this delay of about 6 months before the aerosol spreads out and has full effect. And it actually gets detected, if you like to think of it that way, when you look at the comparison with the ocean heat content. I think that's kind of an interesting result. So how well do these other things agree? Now remember, this is plus or minus 1 standard deviation, so you can double that, and there are times when, you know, there's certainly a lot of fluctuations here, but there are times certainly in here, and this includes the 97-98 El Nino event and also the 1995 El Nino event. Now I've marked on here all of the El Nino events, and so you can see the big dips down here occur at the end of El Nino events typically. And so El Nino is playing a role in some of this variability from year to year. There are times maybe in here when the variability seems to be outside of what you might have expected from CCSM4. So my conclusion here is that maybe this is not a perfect match. Either the variability is underestimated in CCSM4, which I think is a real possibility, or the variability is too large. In other words, there's a lot of noise or extra noise in the ORAS4 data, which is also a real possibility. And we'll get another commentary on that when we look at the series data as well. So anyway, that's the extent to which things agree. So now looking at El Nino events, and we looked at these, and they didn't look to me to be too good prior to about 1992. Well, it turns out there were 2 buoys that were established in the Toga Tau array, one at 110 west and one at 135 west, prior to about 1992. And the Toga Tau array was established in 1992-93. And so we looked at all of the El Nino events since then, and this is the composite of the Nino 3.4. Actually, I think it's the ONI index, but it's basically the Nino 3.4 index. The 1997-98 event actually goes off the top of the scale here. And so there's a lot of spread among these so-called El Nino events, and the composite mean is given by the black lines on here. And then the composite with 1 standard deviation, I think, down the bottom is given here for the global ocean and for the tropical Pacific. So looking at the tropical Pacific, firstly, we'll see that in general, with an El Nino event, there is a drop. There is negative values. There is a cooling of the ocean. In other words, heat comes out of the ocean during an El Nino event, contributing to a mini global warming at the end of an El Nino event, and that is that's in the tropical Pacific. But if you look at the global ocean, you'll see that the whole of the ocean in the other parts of the world as well are affected for at least a year after the time of the El Nino event. And so these appear to be significant in that we've gone from a heating of the ocean before in La Nina conditions to a cooling of the ocean during and after the El Nino event. And it has consequences not just in the Pacific, but also in the Atlantic and the Indian Ocean. Now, I didn't emphasize this in the previous figure, but unfortunately, it's very hard to take apart the volcanic eruptions in the El Nino events because they're conflated. There was an El Nino event at the time, or close to the time, of these 3 volcanic eruptions. And so this confounds a little bit the sorting out of the El Nino versus the volcanic signal. Now what I'm going to do is to look at decadal variability. And so this is an updated version of the Pacific Decadal Oscillation that Adam Phillips produced for me. And here's the overall time series. These are monthly values of the Pacific Decadal variability here. And I want to look at this so-called hiatus period in recent times in more detail. So here's an annual set of the PDO index showing the overall low-pass filtered values, showing indeed the decadal variability in this Pacific Decadal Oscillation, this pattern that occurs. And so we can characterize it as positive phases and negative phases. And in particular, it was positive from 1976 to probably 1998 through the El Nino event. And then since then, we've really been in a negative phase. So this is the period where we've got ORAS4 data, and we've also got other data sets that we can look at. If we look at the GISS surface temperature data set, this is what it looks like when we do the average from 1999 to 2012 versus 1976 to 1998. So this is the period when the so-called hiatus has occurred. So where is the hiatus occurring? My goodness, it's warming in most places. It hasn't warmed much in the Southern Ocean, and it hasn't warmed in the Central and Eastern Pacific and all the way north and south. And in fact, this has the pattern of the Pacific Decadal Oscillation. So this is playing a key role in the so-called hiatus, the lack of warming that has occurred in the 2000s. We can also look, this is now using ERAI data, the ERA interim analyses, at the sea level pressure fields, which is the colors on here in terms of hectopascals, and also the wind field, and this is 1 meter per second up here. And so what you can see are these high pressure regions in here, low pressures here. In fact, a very distinctive pattern all throughout the Pacific. High pressure over here, low pressure over here. The Southern Oscillation is here in force. And let me also emphasize, by going back here, these high pressure regions are occurring right in the regions where the cold sea surface temperatures are occurring. In other words, this is what we expect in the tropics. We expect in the tropics that low pressure goes with high sea surface temperatures, and high pressure goes with low sea surface temperatures, and there's a overturning in the atmosphere, the Walker and Hadley circulations that are affected by this, and you can see the changes in the trade winds, the convergence that's occurring over into this region very actively, and quite strong and significant wind anomalies occurring all throughout the Pacific Ocean here. And remember, this is a 14-year period versus a 23-year period. These are remarkably large anomalies, both in terms of the sea level pressure and in the wind field. And this goes all the way down into the Antarctic. This happens to be the region where all of the Antarctic sea ice has expanded. And in this region here, in the Antarctic Peninsula, is where the Antarctic sea ice has retreated. And up here, where we've got high pressure, of course, this is the Arctic, that's also of considerable interest. And let's see, there's something else over here that I want to look at on a different projection in just a minute. Firstly, just highlight these very large wind anomalies that have occurred over this last, 14-year period. So this is now the polar stereographic projection for the northern hemisphere. So here's this subtropical high that shows up, and then we've got this pattern with the large high pressure over the Arctic region. And the way in which I characterize this is to draw a line like this, which is actually a Rossby wave with a low wave number 1 at high latitudes, or wave number 0 even. And it turns out something like this has actually been simulated in the Hadley Center model in a paper by Einarson and Scaife. As part of a response to El Nino. And so the suggestion here is that disrupting or changing the Pacific through the Pacific decadal oscillation in this particular case has had a connection into the Arctic and across into Europe, where it has affected the North Atlantic oscillation. And the North Atlantic oscillation is in its negative phase here. And what have we seen in recent times? There's been a number of very cold winters that have occurred in Europe in association with this. And we've got a paper which looks at this stuff in more detail, the AMO, the NAO, the PDO, and I don't have time to go into it in any further detail here. What I want to now look at is, well, what about what's going on in the ocean? So in the ocean, if we do, slightly different period, we don't have the data right up to date, but down to 100 meters, this cooling at the surface goes down to 100 meters, and the warming over in the Western Pacific goes down to 100 meters. Now look carefully at the scales here. This is going down to 700 meters. The scale is doubled, and the scale is doubled again when we go to the full depth. The colors here are even stronger than they are here, and so you've got more than double the amount of heat going down to 700 meters. There's a major contribution from 100 to 700 meters, which actually looks a lot like this, and well, actually looks a lot like this. This is basically the pattern from 100 to 700 meters, if you like to think of it that way. And so there's a very strong pattern throughout the Pacific of this cooling in the central and eastern Pacific and the warming in the west, extending well off of the equator in both hemispheres. If we look at the full depth, there is a slight intensification, in particular in the northern hemisphere. So if you look carefully in here, this number here is something like, what, 8? What are we looking at? 8 units. I haven't got the units on here. There are 10 to the 8th joules per meter squared. And down here, this is over 10, maybe getting up to 12. So there's a small contribution to this, but the Central Pacific is not contributing a lot extra here. But the Southern Ocean is, the North Atlantic is, and the South Atlantic is. And so these teleconnections that we were looking at on the previous slide, the PDO in this case, or at least these anomalies that have occurred in this last 13-year period, are not just confined to the Pacific. They may have had their origins in the Pacific through this Pacific decadal oscillation, but they've got imprints at higher latitudes into the Arctic, into the North Atlantic, and into the Southern Ocean. And I mentioned before, they probably have had an imprint also on Antarctic sea ice. This is a picture now with the 3 millimeter per year linear trend removed from the global sea level, from the sea level record from the Topex Poseidon Jason record from 1993 on. This is courtesy of Gary Lagerlof, showing this warming in the west. The ocean has expanded. There's a thermosteric component over here associated with these strong winds, and a deficit in sea level showing up in the central and eastern Pacific. very much aligned with the changes in the ocean heat content. Again, reinforcing with a completely different data set the nature of the specific decadal oscillation pattern. And Gary's done an analysis of this, and the predominant part of this is indeed associated with the PDO. Now with Jerry Meal and colleagues, we put together an analysis of what was going on in CCSM4 for the 21st century during a time when we knew there was an energy imbalance at the top of the atmosphere, and so there was warming going on. And this is a record from 5 ensemble members and the overall average going into the 21st century. And indeed, there are periods when there are hiatus periods in the model. This is 10-year periods when there was no warming going on. And so a couple of them are highlighted here. And in this study, we found a number of these and did an analysis of them. And so the overall trends during these 10-year periods went negative in this particular run, the blue run that's on here. But there were a number of others of these, and we put them together as a composite, and this is the result. So at the top of the atmosphere, the energy imbalance in this case was about 1 watt per square meter, both in the hiatus periods and in all the other decades. But if you looked at the ocean heat content in the model, down to 300 meters, there was a deficit in the hiatus periods, and there was a surplus below 300 meters and below 750 meters relative to the other decades. And we can also look at this then in the other oceans. This is the Atlantic, the Pacific, the Indian, the Southern Oceans, and the Arctic. And in fact, they all have similar things where there's a deficit down to 300 meters and an excess below 300 meters in the model. And so there's 2 papers written and published on this now by Meal et al. In 2011 and 2013. This was in Nature Climate Change. The other one is in the Journal of Climate. It's not quite out. It's out still in, is Jerry here? Yeah, it's almost out. It is out, okay. And this is the pattern that goes along with that we analyzed. And lo and behold, we have the negative PDO pattern in the Pacific. That is the time when the heat is going into the ocean, but going to greater depths and is not manifested at the surface. There are some differences here. We don't have the connection to the Arctic and across to Europe showing up here. We do have the connection down to the Southern Oceans here, although we don't have the Antarctic Peninsula with the opposite phase. But a lot of what is going on in the real world seems to also be going on during these hiatus periods in the model, in the CCSM4. Now, another aspect related to this, I'm just going to touch on it with one slide, is that there was a paper published in Nature Geosciences by Otto et al. And this is the group that had a strong influence in the recent IPCC report, where they were looking at climate sensitivity and saying, well, given this recent record, what does it say about climate sensitivity? We've got a hiatus in the warming. Does that mean something in terms of climate sensitivity? So here's a formula for the equilibrium climate sensitivity. It relates to the forcing corresponding to a doubling of carbon dioxide, the actual observed change in temperature, the changes in the forcing, and the amount of heat that's being taken up by the ocean through or the rest of the climate system to sequester that heat so that it has some impact on this quantity. If you take the values from ORAS4, which are 0.91 watts per square meter when you add in the contributions from the melting of Arctic sea ice in Greenland and so on, compared with the value which they used in their article, which was 0.65 watts per square meter, it changes the equilibrium climate sensitivity from 2.0 to 2.5 degrees C. They also used some rather curious values. They used 3.44 for a doubling of the forcing for carbon dioxide doubling whereas I think a more accepted value is something like 3.75 or 3.7, whoops, what happened there, watts per square meter. And also, if you change from 0.75 to 0.8 for delta T, then the equilibrium climate sensitivity goes to 2.9 degrees C. So there are hazards in doing this with short records, is one of the first lessons. And secondly, there are hazards if you use the wrong data set. They use the Dominguez et al., the Church et al. Data set, and quite frankly, we can't reproduce their results. So this number seems to us to be low. And ORAS4 gives you a lot more heat during the 2000s going into the ocean. So it matters for things like climate sensitivity estimates. Now I want to turn to the series era, looking at the top of the atmosphere radiation. So we've got measurements from series, and here I've got the absorbed solar radiation, the outgoing long-wave radiation with the scales on the right, and then the net is given here. And there's a little bit of arbitrariness here because the calibration of this is not accurate enough. And so I've assigned it a value of 0.8 watts per square meter for the average. So you can move that up and down a little bit if you like. I've also plotted on here the Nino 3.4 time series because that certainly seems to have an influence on this, especially at certain times. And in particular, in 2008, January 2008 is the coldest month this century so far. There was a strong La Nina that shows up here. It was relatively cold. As a result, it was cold through 2009. As a result, the outgoing long-wave radiation was less. At the same time, there was less cloud in the tropical Pacific. So the absorbed solar radiation went up. The combination of these two things boosted the net energy imbalance to 1.5 watts per square meter during this time. So that's the analysis of what went on in association with this La Nina event, and these other fluctuations have a El Nino, La Nina component to them as well. This analysis was, there was analysis by some of the series guys and some ocean guys here in Nature Geosciences, and here they used 3 different data sets from the same 3 that we've used, by the way, but they took simple differences. These are the values which, if you go further back in time, these values are up, well, already here, they're over 3 watts per square meter. This is an absurd way to try and compute the changes in the ocean heat content, quite frankly. So what we've done is to redo their analysis, and now we've got the same 3 on here, along with one from Josh Willis, although that starts using Argo data only from 2005 on. And we've put also the ORAS4 data on here. And you can see that, in fact, there's reasonably good agreement back in here that the energy imbalance was more than 1 watt per square meter for a number of years in the early 2000s back in here. There's discrepancies between ORAS4 and the other estimates in here in about 2005. Argo data is not adequate, it turns out, prior to about 2006. And then after that, you can see there's fluctuations up and down that agree reasonably well. And by using the procedure that we've done, we've also got lower error bars associated with these things. So this is going down, comparing light with light, down to about 700 meters, or in Willis's case, 900 meters. Now I want to go to the full depth so that I can compare with series. So this is now going full depth with series, with several estimates on here of well, let's see what they are. We've got the series in ORAS4, we've got Remick and Gilson, which is an Argo-based product. There's a World Ocean Atlas from Levitas et al., and then there's Karina von Schuckmann's, von Schuckmann and Traun's analysis on here, which is an Argo-only product as well. And so here I've put them together again. The series has an error bar about it, and there's an extra little piece which is associated with, you know, maybe unknown drifts in orbit or changes in the instrument on decadal timescales. and so here's the series record versus the ORAS4 and the other values in recent times. And so in the early part of the record, the ocean heat content, as we saw on the previous slide, was above 1 watt per square meter, and the series values are too low in this particular. I mean, we can move the whole curve up and get them to match better here, but then in more recent times, the series values are too high. And in particular, in 2008, 2009, the ocean heat content is quite a bit lower and significantly lower, so that there's what I would call missing energy in here. In other words, we can't balance the energy budget in this particular period here. And if you step back and look and say, well, how well do these actually agree? You know, you can see that there's some agreement among the ocean reanalyses, but there are disagreements with series, and I don't think there's great agreement between these. And so my summary of this is that there's not great agreement between these two things. They're not replicating each other that well. The ORAS4 fluctuations are supported by other OHC analyses for the most part. At times, there are significant discrepancies between series and the OHC, and I've highlighted 3 of them here. So while the error bars are large, there appears to be either missing energy or there are mismatches between the series and the ocean heat content. Well, another way of saying that is, well, the error bars should be larger. That was basically the conclusion of the Loeb et al. Paper, that the error bars are so large that, in fact, neither of these 2 data sets have any value whatsoever because all of the fluctuations are within the error bars. I find that very hard to accept, and so we've been working very hard to get what we can out of these things. And so here, this is part of the challenge. Last time we did this, a few years ago, both of these guys, or the series guys, revised theirs, and they changed their results by about 15 to 20%. The ocean heat content community, all of them, have reprocessed all of their data, and they've changed all of their values by at least 20%. So they've got another 20% or something to go, I think. But, you know, maybe we're getting there slowly by putting this kind of comparison together and pointing out that, you know, we need to do better. So from the linear trends from the ocean heat content from ORAS4 are given here. In the 1990s, with the Pinatubo and then the 97-98 El Nino, there was actually a loss of heat, 0.84 watts per square meter on a, this is the global number, this is the global ocean number, and then you can convert this, as I already mentioned actually, when you include melting ice and other components, 0.07 watts per square meter to give you 0.84 watts per square meter for the 2000s. So if you want to do the sum, 0.07 versus 0.84, you can see indeed that the ocean is taking up more than 90%, 92% or something like that of the heat associated with the energy imbalance at the top of the atmosphere that we're inferring here. So some other comments on this. During the last decade, the ocean has warmed at a higher rate than in the preceding record, even when the impact of Argo is taken into account. I didn't have time to go into that. We've done a number of, or Magdalena's done a number of studies where we've done some experiments by dropping Argo out. And it turns out you can still replicate this because a lot of it is associated with the winds, and it comes from the sea surface temperature analyses and information which is not dependent upon Argo. So about 30% of this warming is occurring at depths below about 700 meters, and the involvement of this deep ocean is unprecedented. It's only occurring in the recent times. Now, is that because of Argo? Now, I suggested to you that it's actually occurring after 1998, which is before Argo, and so we think it's actually associated with the negative phase of the Pacific decadal oscillation. In other words, it's physical rather than instrumental. The volcanic eruptions, ENSO, contribute identifiable signals to the character of the ocean heat content changes. And annual values of ocean heat content are simply not adequate. This is what other groups have produced. And differentiating them to get rates of change provides a real challenge to the community to start to get those right. The increasing disparity is very much related to the changes in the surface winds. So the ocean, the overall energy imbalance at the top of the atmosphere varies from day to day with clouds and weather. It varies from year to year with ENSO. There are sharp drops in association with volcanic eruptions. It varies with the PDO. And the net imbalance in the 2000s went from, order of 1 watt to probably, well, maybe even a little less than this, because something beyond the radiative forcing contributed to this with the quiet sun and minor volcanic activity. But the contributions of those are up to about 0.2 of a watt per square meter. So most of what's going on here is association with the PDO. Some of the missing energy appears to be in the deep ocean, and the unprecedented heating of the deeper ocean is occurring, and it's very much related to this La Nina and the negative PDO phase. During the positive phase of the PDO, we think more heat is being deposited at shallow depths. So this occurs from 1976 to 1998. And so we see larger warming than you might expect if it were fully distributed throughout the ocean, while in the negative phase of the PDO, more heat is deposited below 700 meters depths. And I think there's a lot of interesting work related to this, and it also emphasizes the need to get the PDO and the specific decadal variability correct in our climate model. After we published our article in GRL, this woman, Lynn Page, sent me a limerick, and she said, I write limericks. You can go to her website here. And this is the limerick she sent me. She said, there's a clearer analysis forming of the increase in powerful storming, but it's not just hot air about which we should care, for the cold ocean depths have been warming. I thought this was pretty good, Somebody said, where's the title? She didn't include a title in the email that she sent me. And she said, well, she thought about this, and this was the title that she suggested. And I cracked up when I saw this. I thought this was absolutely hilarious, because with this problem, with global energy imbalance associated with global warming, we are in deep doo-doo. Thank you very much.